I'm Sam Fletcher. I'm the chair for this afternoon session. The first talk that we have this afternoon is Professor Claudia Maraston, who is from the University of Portsmouth, and she'll be talking to us about elusive light, dualism, and natural limit. Please, Professor Maraston.
Thank you very much. I first would like to thank the organizer, because this is not my usual natural environment, and I've learned so much during the morning session, and I really hope that I can give you something. The other thing that I would like to say, Joanna gave me a title, and that's the title that is printed there. Let's say I made it up a little bit because of the longer time span between your kind invitation and the actual realization. So quantum mechanics entered the way. No, thank you. So yes, I will try to cover the task of covering historically how we got to the speed of light and the implication it has on modern theory for the universe and the microphysics. I am an astrophysicist, and therefore I will also take you into the major implication and connection that exactly this type of theory has on our understanding of the universe. And in fact, I start by showing you the oldest ever emitted light in the universe, which is the cosmic microwave background. It is here shown as a temperature map. The difference in temperature are tiny, of the order of 10 to the minus 4, even less. That's a strong probe of the homogeneity of the universe at that epoch. But before that epoch, there was no light, which is, if you like, another problem we should be discussing. That's the first thing. This was emitted 400,000 years since the Big Bang. So we go back to really the start of things. Before there was no matter and there was no light. So if you like to see big numbers, as astrophysicists are used to, that's the currently accepted value of C. When I give problem to the students, I round this up to 300,000. Do we need all these figures? However, they are actually experimentally verified. So the question is, how did we get there? Also, I wanted to give you the information that, I don't know if you wonder why we call it C. C comes from celeritas, which is speed in Latin, something I studied when I was studying in Italy. So we have had several points of discussion in the morning towards the history of whether light should propagate at a finite or infinite speed. The number I just showed you, it's quite close to be a huge thing. And I tell you, the experience in astrophysics is that these numbers, when they become too large, they almost tend to infinity. However, it was everyday experience that light and sound propagates at very different speed. And that's very simple if you think of a thunderstorm, in which you see the light immediately, and you wait a little bit to hear the sound of the thunder. And then according to how close they are, you better find some escape, because it can be bad. Does this mean light travels at infinite speed? It only means it travels faster than sound. So I think this was the question that anciently people started to think about. So one of the first, and I hope the historians in the audience will agree, but please feel free to correct, we find this type of speculation back in ancient Greece, but actually in Sicily, in Agrigento, where Empedocles came from. And he said, he was meditating, and we know this mostly from Aristotle, that the light of the sun must take some time to reach the Earth. We actually know it's about 8 minutes. So its speed must be finite. This is what he concluded. A sort of less than 100 years before Christ later, Aristotle was being quoted for this sentence. Light is due to the presence of something, but it is not a movement. For which people have concluded that Aristotle actually was supporting that the speed of light is infinite. So we are already with this dualism, which is not the classical dualism, problem already back centuries, millennia. Heron of Alexandria added their bit in working in Egypt, in North Egypt, in Anno Domini 62, and he said, well, the speed of light is probably infinite because when we open the eyes and we look at the stars, this is a beautiful image of the Milky Way, we see stars instantaneously. There is no delay. So you see, you find a way to probe your thinking, and we still proceed this way. The problem is, if something is infinite, are we able to measure it at all? Does it make sense to define a measurement in this sense? So, with a bit maybe of quoting that I'm not reporting, this notion of infinite remained until the early 17th century, with two quotes from two famous researchers, one astronomer and one mathematician, that have been quoted in the morning session. Kepler, to which we do, in fact, we own the Kepler law for the movement of planets, came to the conclusion that if the speed of light was finite, the sun, earth, and moon should be out of alignment during lunar eclipses. As this didn't seem the case, then the conclusion was that it was not finite. Descartes agreed with Aristotle, and in fact, he went that far, apparently, to postulate that the speed of light is infinite and may even be speed up through certain type of media. The first experiment to try to measure the speed of light, however unsuccessful, is due to Galileo Galilei in 1638, which envisaged an interesting experiment, namely himself and an assistant on two farther away, but not more than 2 miles, hilltops, with a lantern covered by a cloth. And so the experiment consisted in removing the cloth, and the assistant should have immediately ticked something, I don't know what they had at the time, to say, oh, well, okay, that's the time delay, and therefore then you can work out the velocity. The experiment failed for several reasons, but I think mostly the distance was very small. And the reaction time of the assistant is assistant dependent. It's not sort of an objective experiment. And Galileo, in fact, said that he was not aiming to really get, so he was able to find a way out of this failure. But that has changed actually mindset. It was mentioned in the first talk, we actually owe the first measurement of the speed of light to Euler Riemann, who was active in Paris and actually an assistant of Cassini. And I want to mention this because there is an interesting story behind, who in 1676 used the moons of Jupiter and especially Io, and the fact that they had different duration, whether the motion of the Earth was approaching or receding from that other planet. And that implied, in fact, different light paths. And so he concluded with this sentence that he did not provide apparently an actual number, but he said this inequality appears to be due to light taking some time to reach us from the satellite. Light seems to take about 10 to 11 minutes to cross a distance equal to the half diameter of the terrestrial orbit. And that's the thing that he published officially. What I wanted to say, Cassini, well known for the Cassini telescope, who was his mentor, actually found mathematically with this measurement this type of oddities before, but he decided not to believe to that. And that's an interesting thing, right? So the student instead decided, okay, instead I think this is telling us something. And the other one was, in a sense, too conservative and decided to leave it go. And now we know how it goes. I found this very interesting. So we can proceed towards modern measurements, and excellent reviews have been given, in fact, before lunch. There are a joint effort from two apparently competitors, Fizeau and Foucault, in 1849. They already used terrestrial laboratories. I wanted to say Euler Riemann also is distinctive because he thought that, in fact, the speed of light has to be measured in space. Because just space gives you exactly the span in size. Not in time, because we are speaking about the local universe, but in size to make this measurement significant. So they instead, where we are already at the end of the 19th century, mid of the 19th century, they had the facilities to do this in lab. And they found the sea, which is quite very much similar to the actual current value, which to me is very it's impressive. So what do we conclude about this number? Well, C is huge. It's outstanding, right? Think about when you are on your car, if you would like to drive that way. But it is finite and it has a number that we can work with. I think that's a different thing. Now, these two gentlemen, Michelson and Morley, actually changed history by performing an experiment whose results are not what they were seeking. Working at Case Western University, they wanted actually to detect that substance called ether that has been mentioned before lunch. And so, in the assumption that you can, in fact, detect emotion with respect to these things that you don't see but is there, then the difference in the velocity that they would measure would be detectable. But the experiment failed. It is interesting because being an astrophysicist, I immediately thought about dark matter. And I want to throw this for discussion. Because when we speak about dark matter, which is 30% of the universe, and I will come back to that, we don't know what we are talking about, and we say instead it is not ordinary matter. It's nothing like anything. And it is there. And so this failed in the sense that there was this proved that the ether was existing, or the other way, you say the speed of light doesn't change with respect to the movement that is carried of the source of light. And that will have a catastrophic implication on modern physics. And so obviously then the next step that also was mentioned before, it is a great program that the organizer have written down, because all talk to each other. It's very nice. So 1905, the year of special relativity. The speed of light is central. This was a question during the morning session. It is central to Einstein's theory, as I will also show, also to the evolution of stars and actually the light source in the sun. But it comes a bit as a postulate of relativity. Namely, the speed of light in vacuum is the same for all observers, regardless of the motion of the light source. So, crucial, because it is a postulate. It's like when we postulate the Big Bang, the hot Big Bang. Also, the laws of physics are invariant in all inertial frames of reference. That's just for completeness. So C enter in the core of the definition of these theories. And so, again, in the topic that I was asked to cover, I will briefly point out some thought on the relevance of the speed of light to relativity and to quantum mechanics. So, it is completely intrinsic to relativity. It is one of the postulates of our current major theory of space-time. It also implies, for another reason that will be in the next slide, that C is a natural limit. Heavy word to say, both natural and limit, but this is the way we would like. Because the fact that C is constant and C is space over time implies that the time is no longer an absolute. And simultaneity is a relative concept. And that was absolutely catastrophic. When I studied it in my secondary school, I liked that because it was mind-blowing. I mean, in the sense, I'm sure that most of us still don't get it. We accept it, which is a different thing. But it's fantastic. So time is not an absolute. Also, when you approach the speed of light, you have this fantastic twin paradox of time dilating and clock proceeding slower. So astrophysicists verified this with quasars that are emitting supermassive black holes. It's ordinary thing. Fantastic, but and also, and that's another consequence, if you could travel faster than the speed of light, times start to run backwards. And that's a problem, might be a problem, because this breaks causality. So, in fact, I bet that there are also those who do not like the fact that we have this constant. In physics, we have a lot of constants. And we were discussing over lunch, some of these constants, are they really constant? Are they constant in our universe, in the assumption that there might be others? Or are these constant because we have not yet found a way to actually invalidate their value? So far, they are brilliant constant. So this equation is fundamental, and that's the other connection to relativity. This tells you it's the simplest equation that you can teach the student. The student always remember that. It's brilliant. E equal mass. Energy and mass are the same thing, but a constant. And the constant has that value. But it has to have that value if you want to explain the luminosity of the sun. And that's nearby, and you measure it. So the nuclear reaction, the fact that the sun is now currently converting hydrogen into helium, it does so with this equation and a convenient factor, which gives us the right energy per time. If you change that, you need to change several other things. But especially, that goes back to Empedocles and probably many others. I'm not a philosopher, so I quote just what I know, what I think is safe. That you don't create or destroy, but you transform. And this is fundamental. So I quote just for your leisure, the energy lying within the sun or within a person, order of magnitudes of difference. I will come back to that towards the end of the talk. Speaking about quantum physics, just a brief homage to this fantastic theory, very mysterious, as the speaker before lunch said, that would like to link matter and energy at the most fundamental level. And as it was already said, according in that theory, light and matter both consist of particles which have wave-like properties associated with them. Okay? So we know the entity for light is called photons, and there are many other particles in the Standard Model, and many more to come. The Higgs boson was just made a few years ago, a few decades maybe. So one thing that we astrophysicists use all the time is the fact that C enter in defining the energy of these photons that we receive from space, with, again, another super clean, elegant formula, E equal h times frequency, which means times h c over wavelength. H is another constant of nature. I won't talk about that. It's the Planck constant. But there is also this connection in this formula of two fundamental constants, but one is the speed of light. So that's the other relevance. And this is crucial because, and we see this, I will show you a spectrum of actual astrophysical objects. The energy level are not a continuum, they are continuum in approximation of infinity, but they are actually discretized. And if a pattern of light does not have the right energy to excite atoms, it won't do anything to them. That's all contained in this formula, which depends on two constants, and I acknowledge Niels Bohr and this atom model. So, here I use the term elusive, probably incorrectly in the sense I use it in the real adjective that it means to me, but it seems that there is a theory on elusive light, and I'm not going to that. The uncertainty principle is another thing that I personally liked very much when I was studying. And this tells you that, as we know, it is impossible to fix in the same experiment the position and the momentum. But what is the momentum? Mass, time, velocity. You have to decide whether you have massless particles. In that case, it's becoming trickier. But in principle, that's the link. So this was shown already. The photoelectric effect in particular really probe the wave and particle dualism of light. And so I can go on. And now let me go into the astrophysics. Who of us didn't dream at some point to travel back on time? I think about this all the time. And in fact, here it's me at 2 years and a few decades later. So So maybe this is why I did astrophysics, because astrophysics naturally is a time machine. Because the distances are so huge, when you move into space, you automatically move back on time. And this is the usual cone of the universe, a cylinder in this case, that show you actually the various epochs and the expansion of the universe from inflation. The first light emitted that they call afterglow, this is a bit, but it's a cosmic microwave background, something dark in the middle that we still have to understand, and then comes the first stars. The stars are using E equal mc squared to pull out their energy, and they illuminate the darkness, and then you develop galaxy, planets, whatever, and where you see the name of this satellite, we are at the local universe, and I also position in space-time the birth of our sun 4.5 billion years in the past, and our Earth. So anything that has to do with astrophysics has to use C, simply because everything is red-shifted, and time is going backward. So things are extremely connected. We could not do without. So another relevance to astrophysics of C is the realization, really due to Arthur Eddington in 1920, that the energy in the sun must be sourced by something that it was not yet clear in 1920, that is able to convert 5% of the sun. Nowadays we know it's about 10% of the actual mass of the sun, fusing hydrogen into helium, and it was the only type of energy with this equation that would give you the right time scale. So I give you a time scale of evolution of 10 billion years. So in this sense, if we change C, this time is going to change. But we have probes on Earth, on fossils and rocks, that our planet is obviously as old as the sun, or more or less. So this is really important because these are numbers. If you think there is no source of energy in the middle of the sun, if I would be able to switch it off now, the sun would collapse under gravity in 2,000 seconds. Again, if you don't know, if you, again, exclude this E equal mc squared within the sun, and if you think the light of the sun come out of thermal energy, namely it's a heated body is giving away its energy, that all would last 30 million years. So you see, the scale of the order of magnitudes of time scale never worked before this equation was written. And now we use it to calculate the complicated things for galaxies up to the dawn of time. So this is the spectrum of light of a galaxy. I have to tell you something that I do all the time. Because it was mentioned earlier when speaking about colors, about the continuum, and then you see. So essentially what these huge assembles of stars do for us, they give us flux on the y-axis, arbitrary units, as a function of wavelengths with no breaks. You have your spectrograph and you collect that. And I just quoted the quantum nature of this spectra implies that the lines are actually uniquely associated to elements transition, which allow us to get the chemical composition of galaxies up to close to the Big Bang, if you're able to get this spectrum. So you see iron, magnesium, all ordinary elements, titanium oxide, sodium, and calcium. You connect this, it's a continuum. I never thought about the colors the way it was described in the morning, so that was interesting. Because for me, all the colors are in this line, and there is no break. But I don't give them name. So this is an observed spectrum, and this is a model spectrum, and I wonder whether this was supposed to be a movie, actually. But I don't seem able to. No. Okay. You will have to renounce that it's at my webpage. So these are my theoretical spectra with a resolution even better than the observed one, which are calculated using C, using H as they are, and some plasma physics. The constant are where they are. The number there is a time scale, and this means 3 million years. And that's the emission normalized. And this is how a galaxy evolves. So the movie, if it would have worked, it would have shown you those things, but probably we don't need. That's why, related to this conference, they are called the model of light. So we astrophysicists in jargon, we say, what is the light of that galaxy? How much is the light of that galaxy? We speak like this. It is actually the spectral energy distribution. So, and I'm approaching the end, and I will match the time. Of course, black holes. These 3 colleagues got the Nobel Prize last year, 2020, for having probed that the dynamics in the inner part of the Milky Way is most likely, probably uniquely explained by a hole with mass of 4.5 million of solar masses that provides the distortion that is needed to explain this funny dynamics of central star. You won't see a black hole. So this is interesting because astrophysics rely, as I will show in the last slide, on objects that have no match, no vicinity to light. They are dark. So the gravity here is so strong that it is said in a popular way, but it's right, not even light can escape. But that's because the C has a limit. If that limit would not be there, the physics of black holes would change, most likely. And this is my last slide, and I wanted to throw some food for thought. Arianna, before the lunch, concluded with the same way, and we didn't talk about that, because is this the end of the story? Because the problem for us is that actually 95% of the universe is dark, and there's no relation to light. We call dark matter and dark energy, and they are vastly disproportionate with respect to the baryons that are just 4.6% of the matter. Because, why do we call it dark? Because they have no relation to light. They don't emit, they don't perturb, they have nothing, they don't have interface. But that's this is a problem we have. And the funding agency keeps supporting these researches, but in fairness, there might be an error behind there, because it's 95%. 5% is the thing we know, the normal matter, the one that interacts in goodwill with photons. And I think I leave you with this slide. Thank you.
Thank you, Professor Maraston. We have about 16 minutes for questions. If you have a question, please raise your hand and wait for the microphone to arrive to you so that folks online can hear the question as well. Over here.
Thank you. Yes, an interesting historical tour, and I was struck when you mentioned Descartes, saying that he agreed, I think with Kepler, that the light travels instantaneously, but I was a bit puzzled by the subsequent comment that he thought that maybe light even sped up, depending on the material. Well, if light travels instantaneously, then there is no variation.
Well,
Yes?
that's how, it depends how you, I agree, it depends how you define infinite, if it is infinite plus infinite or infinite to the square. Mathematically, you can do a lot of stuff. No, he was a mathematician, I agree with you. That I just quoted
Physically.
for completeness, I'm not even sure that we should pay too much weight on that, I completely agree with you. If something is infinite, that's it, that's the actual limit.
Thank you.
Yes.
A question in the front. If you could wait for the microphone, please.
Sorry.
So just a quick question.
Yep, go ahead.
How were these figures calculated? How did they realize or that? Not
Yeah, that's a very good question. And in fact, before, when I was preparing the talk, I was thinking, now I need to explain. So dark matter is something that actually came out in the 50s thanks to the work of Vera Rubin that was measuring velocities in spiral galaxies proceeding from the center of the spiral, which has a circular structure plus the arms, towards the outskirt. Now, the Kepler law, and also the fact that there is little matter there, would say that your velocity will decrease proceeding towards the outskirts, where the density is lower. And instead, she found, as a surprise at the beginning, but this was a systematic, a flat rotation curve towards the end of the light, well out of the luminous distribution in galaxies. That means that there is something that sustains that velocity, because the velocity comes as an equilibrium between the potential, right, and the forces towards the center, that sustain the velocity but has no direct connection to light. And so I call it dark matter. This study went on systematically, and essentially, in order to explain the value of the velocity, that roughly 30% was found, in about 26%. This very number comes from the Planck satellite, which is a recent mission. And what they do, they fit with a cosmological model with many parameters, including those figures, the profile of the cosmic microwave background. So the first light that I showed at the beginning. You obtain the spectrum of that light with the satellite, is in the microwave, and then you fit the profile with a multi-parameter fit. And the only good fit you find is for these values, especially dark matter. Dark energy was actually probed in '98 through light, and this is very interesting for this audience. What these colleagues in the US, Perlmutter and collaboration, found was that supernovae, which are exploding stars, distant in space-time, would appear fainter than the theory of stellar evolution would predict for those type of stars. But fainter in a way that means that the universe is not only expanding constantly, but it's actually accelerating. So you derive a term that tells you that there is an energy that gave a push to the expansion of the universe, supposed to be at constant speed, in terms of acceleration. This push was measured empirically through the light of the stars. It's like if you have a candle in your hand, and I'm here, and you are there with the candle, and you start to run away and accelerating, and I measure the light of the candle, knowing what it would be intrinsically. That's a probe. Now, but why we call it dark energy? Because to accelerate something, this is normal laws of Newton, you need to provide an energy. Otherwise, the motion is inertial. And so, in '98, so very recently, I did my PhD in '98, this other problem came, that not only there is dark matter, but there is dark energy. And dark energy is 70% of the budget, so it's catastrophically large. So the sum of them, they have both been detected via experiment based on light, so the supernovae or the light of the spirals, but they don't interact with light. So I think they are quite precise. They also give you the age of the universe in this way, which has evolved a little bit since my PhD. Currently, we think it's 13.67 billions of years. And it is a good number out of those parameters.
Great. Other questions? I have a question, actually.
Yes?
So, since the 1980s, the International System of Units has defined the meter as the length that light travels in a second. So, since the 1980s, there's a certain sense in which the speed of light has been fixed by the way that we understand our dimensionful units, our units of physical quantities. If that's so, what could it mean to have an alternative theory where the speed of light varies? If by our very system of units, we've set the definition of the speed of light in terms of the distance, that we've defined the quantity that light is supposed to travel over in terms of some fixed number in our system of units, namely a fixed speed of light. Do you have any insight about what it can mean, therefore, to have a variable speed of light?
So I mentioned a bit before, and you point to the right direction. E equal mc square. It completely explains the light received by the sun and its constancy over 4.5 billion years, together with nuclear physics. But there is a numerical coefficient, which I didn't write down, which depends on the nuclear reaction that you are considering. So for conversion of hydrogen into helium, this is of the order 7 in 10 to the minus 3. So the way out could be to consider the product of this coefficient times C. Then C can vary a little bit, provided you vary the other one, changing maybe the equation of state, such that their product and the mass of the sun remain the same. So there is a bit of space. But not within the theory of general relativity for the space-time and the whole metric of the universe. That's more tricky. So I think the link to the nuclear physics can do it. We are also discussing changes to the gravitational constant G, which is, again, one of the pillars, making a field rather than a constant. I think we can work out a few solutions, but probably not the big one. That would be my opinion, but this may change.
Yeah. Please, go ahead.
Hello, I'm
Hi.
sorry I was a little late, but I enjoyed the bit I got to see.
I didn't notice that, but thanks for saying.
But one of the things, I'm going to throw a hand grenade at you, if that's all right. So we've defined the speed of light as a constant, and let's just assume that well, I'm pretty sure it is. But there's nothing to say that it's the same speed in both directions. Because in order to have information transfer, that's the limit of that is the speed of light. Right, so in order for me to know that you've got my message, you have to send something back. And that whole process is limited by the speed of information, which is the speed of light. So obviously light could change in, say, a medium, but the speed of information is fixed.
But that's the information speed. No,
Yeah.
I agree with you. Yeah, that's
Right,
very
so
insightful and modern.
But what if the universe had a sort of a fast axis, or something that was in one direction? So you can imagine like light was traveling twice the speed in one direction and infinitely fast in the opposite direction, so that the round travel time is still the same. And obviously you have a plurality of different options within that sort of, you have an infinite number of options actually, but we just arbitrarily decide that the speed of light is fixed and it's the same in both directions.
But that, yes, go ahead.
So the question as an astronomer is, I was wondering whether if somebody said to you, like maybe me right now, is there a fast axis in the universe? Could you say, well, we can sort of decide on how old the universe is from our imaging, and actually in all directions it's consistent. Do you know what the error is? Can you put bounds on what the difference in possible speed might be?
Excellent mountains of questions, because this is actually, some things touch really directly onto the research we're doing. So in principle, all our construction of the universe is based on two principles: that the universe is homogeneous and it is isotropic. And therefore, assuming that the light behaves differently in different directions is a problem in general, because it would make cascades into other situations. Images of the universe on the largest scale, and the CMB, the cosmic microwave band, is what I show you. The difference in temperature, meaning in energy, is visible. In fact, you need to measure it with a satellite. Testify that at least up to that epoch it is homogeneous. There comes the light, though, so there is still space to change things. In fact, exactly the other day at my institute, a speaker from Nottingham was arguing that to solve the problem of dark energy, maybe we should give up the hypothesis that the universe is homogeneous and isotropic to solve exactly that problem, so the things could be really. But nobody wants to give it away because it is at the core of the hot Big Bang, and the hot Big Bang is verified with a few probes. Measure, for example, the helium abundance in the halo of the Milky Way is spot on what is predicted by the hot Big Bang for the rate of expansion that we measure. The other problem we have, the universe is actually flat, so it cannot collapse on itself, which touch upon your way of the light going back and forth. The big crunch should not happen if these measurements are correct. So your speculations are correct because all of what I'm saying are principles, postulates, right? And there are several in cosmology. So we may give up this and explore other avenues. You're welcome to help. Yes.
Yep. The next question's over here.
Taking up the last question about the speed of light not being the same in both directions, was that not answered nearly 150 years ago with the Michelson-Morley experiment? Because, for example, if you drive from London to Birmingham 100 miles, you go at 100 miles an hour there and come back at 50 miles an hour, your average speed isn't 75 miles per hour, it's 66. And so it demonstrates that the speed of light is the same in both directions.
Well, that is not really approaching the speed of light.
This sounds like it'll be a great break discussion. We have just time for one more question, though.
Well, I'm in a dilemma now. I just wanted to comment on that. We know the speed of light is dependent on the permittivity and the permeability of space, and that we can measure. So you don't have to wait for the signal to come back. You can just measure it in one direction, and that's constant. No?
You need to know what you can't do that, because in order to measure 2 points, we have to send the information back.
Wow.
So if you have infinitely slow, you could do it.
We'll discuss it later.
This is very interesting, and I don't have...
Sorry, can I just ask, you said before that dark energy has got nothing to do with light, but we know as the universe expands, the light is stretching with cosmological redshift.
Yes.
So dark energy is gaining energy, but at the same time, the light is losing energy because frequency is equal to energy. So isn't that light loses energy, dark energy gains energy, so it's equal. That we haven't gained, we haven't lost.
No, but I mean, dark energy seems to kick things, for example, at a certain epoch, which is a coincidence problem, but in itself is not an energetic term, related to light. Okay, there is no interface between dark energy and baryons. There is no interaction. So it is a form of energy, but we think it's not ordinary physics. It is something else. It may be the equation. There is an equation term that gives us a value that is -1. That would be the cosmological constant. Okay, this is one hypothesis, but it's not the only one, actually, that we have. But it is not really, it was probed through light, but in itself, as a nature, it should not be connected to light.
Okay.
Great. Thanks so much for the lively discussion, everyone. Let's thank Professor Maraston again.